Let's work on this problem that we see here from chapter 10, number 14. We're trying to decide whether or not to purchase a new handheld laser scanner for use in inventorying stock. Tests are conducted on the scanner currently in use and on the new scanner. And these data are obtained on the number of 7-inch barcodes that can be scanned per second. We've got two independent samples from two populations is the idea. Population 1 consists of what happens with the old scanner when you try to figure out how many barcodes it can scan every second. Population 2 is with the new. Actually, I guess I have it the other way around. The new one is the first one and the old one is the second one. We've got two samples. These samples you can see are both size 61. That doesn't have to be the case that those are always equal. They just happen to be for this example. Sometimes they are different. You might even say most of the time they're different, that the sample sizes are different. The formulas I'm going to show you still work even with different sample sizes. What are we trying to do? We're wondering probably whether the new method is better than the old. Maybe that is our research hypothesis, that the mean mu1 for the new is better than the old, bigger than the old, mu2 for the old one. We do have some evidence for that based on sample means. X1 bar, you can see, is definitely bigger than X2 bar. So it seems like that's probably some evidence against the null hypothesis that the two population means are the same. But the question, as always, is it statistically significant evidence? Is it unlikely to occur by chance? Is the p-value small? The probability of observing a test statistic, whatever that happens to be, as extreme or more extreme than what we actually observe under the assumption that the null is true. The null is like the assumption of innocence in a trial. We assume it's true until proven otherwise. Though it's like you are the prosecuting attorney, you are typically trying to prove otherwise. But you want to have a strong case. You don't want to reject the null unless you got good evidence. When you are comparing means like this, there are some technicalities that come into play that determine what formula you use. And those technicalities are related to whether the population variances are the same or not. And in the directions of this problem, you can see part A, we're not testing means, we are testing variances. And I didn't remember this, but I would mark myself very, very wrong there if I wrote that on a test. Sometime in the past when I wrote this, I think I tried to put Greek symbols in there, but it didn't work. These are supposed to be sigmas here, not S's. You never, ever, ever put statistics in hypotheses, right? That's a never, ever, ever thing. There, I did it. I made this PowerPoint like, I don't know, 15 years ago. I think I had tried getting sigmas in there and it didn't work. Those should be sigmas. Pretend those are sigmas. Those are supposed to be population parameters. That's not a test of the means. That's a test of the variances. The null hypothesis is really sigma 1 squared equals sigma 2 squared. We're wondering, are these population variances the same or not? The alternative is that they're not the same. And actually, so this is a precursor to testing the means. And actually, in this case, it's like you are the defending attorney. You hope they are equal because that makes things a bit simpler. You hope these variances are equal. You hope you're not going to reject the null. And to facilitate your lack of rejection of the null, okay, well, this will actually not facilitate it. Alpha is set at 0.2, which would make it more likely to reject the null, actually. Okay, in general, maybe you want to use a smaller value of alpha, so it makes it harder to reject the null if you hope that the null is true and you make things simpler. We're going to test this at the 0.2 level. How? We need a test statistic. What's the test statistic here? It's one we've never seen before. It's called an F statistic. We've never heard of an F statistic before. It's a new kind of statistic. It's a new kind of random variable. How do you compute the F statistic? And does it have any degrees of freedom? It's got actually two separate degrees of freedom. It's going to be written as a fraction with a numerator and denominator. The numerator is going to have a certain degrees of freedom, and the denominator is going to have a certain degrees of freedom. And looking at the sample variances, we see the one with a subscript of 1 is bigger. You always typically want to put whatever one is going to be bigger on top. You don't know which one that's going to be ahead of time, but we can see here after the fact that the sample variance for population or sample 1 is bigger than the sample variance for population sample 2. It's a ratio of two variances, two sample variances. These sample variances are statistics, and therefore F itself is a statistic. And the numerator has degrees of freedom N1 minus 1. And the denominator has degrees of freedom N2 minus 1. So the N1 minus 1 is the first subscript on the F. It corresponds to the so-called degrees of freedom for the numerator of this fraction. And the N2 minus 1, the second subscript, corresponds to the degrees of freedom for the denominator. Do you need to worry about what degrees of freedom means? Not really. It's just a label. It does determine how you use this F statistic, if you use the table in the back of the book or if you use technology. But that's what it equals. And now we can go ahead and compute its observed value because we've got the two values that you see, 24.9 and 22.7. And do notice those are variances in the problem statement, not standard deviations. Usually in a problem, if you have to figure out the standard deviation, you want to take a square root of a variance. If we're given if we were given standard deviations instead of variances, we'd want to square those to get the variances. Anyway, what does this number end up being? 24.9 divided by 22.7. It's about 1.097. Okay, well, who cares? What is this all about? We're trying to decide, are the population variances the same or not? What would be strong evidence against the null hypothesis? Well, one bit of strong evidence against the null would be if the numerator here was a lot bigger than the denominator, like maybe twice as big or 3 times as big, giving an F statistic of 2 or 3 or so. Well, guess what? Our observed F statistic is not much bigger than 1. The numerator is not much bigger than the denominator here. Probably this is not very strong evidence against the null. You want to be able to think intuitively about these things. Probably this is not very strong evidence against the null. Probably the p-value is not very small. Probably we're not going to reject the null. But if we want to be more sure, well, then we should compute the p-value. A one-tailed p-value, you could label it a right-tailed p-value in this context. I mean, we're ultimately going to compute a two-tailed p-value, would be the probability that F sub, well, what's N1 and N2? They're both 61, chosen so that when you subtract 1, you get a nice number, 60. F sub 60 comma 60, what's the probability of that being greater than or equal to 1.097? Okay, let's go ahead and use the table in the back of the book. The F table in the back of the book is a bit strange. It's probably the strangest table there is. The little gamma 1 represents the degrees of freedom of the numerator, and the little gamma 2 represents the degrees of the freedom of the denominator. And you see you have different degrees of freedom across the top and the bottom, or the side. And in this shading of this part of the F table, you see that the area to the left is 0.9. And what these numbers are critical values. They are values of little f along the horizontal axis. It's a right-skewed distribution, kind of like a chi-square distribution, for example. And what do we have for our degrees of freedom? 60 and 60. Well, across the top here, it only goes up to 10. Across the side here, it does go to 60 right there. Oh, we need to keep paging over. It goes onto the next page where the degrees of freedom for the top gets higher and higher, and onto the next page where they continue getting higher and higher. Do we get to 60 degrees of freedom? Well, on this page, we finally do. 60 degrees of freedom for the numerator, 60 degrees of freedom for the denominator, and the critical value is 1.395. What does that mean? 1.395 for 60 degrees of freedom on the top and 60 degrees of freedom on the bottom is the critical value, such that, going back to the other page, this area is 0.9, meaning this area is 0.1, meaning our number, which was 1.097, has an area to the right bigger than 0.1. That's a lot of work to say that this one-tailed p-value is bigger than 0.1 because it's an area to the right. Should we say the two-tailed p-value then is bigger than 0.2? That's a right-tailed p-value. Well, yeah, let's say it's 2 times the probability of f60 comma 60 being greater than or equal to 1.9097. Now, is that really a valid calculation? Approximately. It's not a symmetric distribution, so it's not really super precise to say this is the p-value. But we go ahead and use it as a convention anyway, even though the distribution is not symmetric. For the two-tailed p-value, double the one-tailed p-value. Let's see what technology gives us. If I go to my distribution menu, go scroll on down to, oh, there we have it. There's an FCDF. I don't know if you've ever noticed that before. FCDF. We want a lower value of 0, an upper value of 1.097. Degrees of freedom for the numerator is 60, degrees of freedom for the denominator is 60. In this case, these DFs are the same, but in general, they don't have to be. This is going to give us a CDF value. It should give us somewhere in the ballpark of, I'm guessing, 0.7, 0.8 something. That's my guess here. Less than 0.9. 0.64, okay. 1 minus that should be the one-tailed p-value. It's bigger than 0.1. It's actually about 0.36. Doubling that would say the two-tailed p-value in this scheme of doubling it is about 0.72. Definitely bigger than 0.2. Definitely do not reject the null. We don't have strong evidence against it, as we expected. Again, this doubling of this one-tailed p-value is not really a perfect thing because it's not a symmetric distribution, but we don't really worry about it. We're happy. We're not going to reject the null. This is a context where not rejecting the null makes us happy, because now when we do the other thing, the main thing we want to do, test the means, it makes things a little simpler. What do the rest of the directions say to do? Part B says to find, what's this? SP squared? What's that? That's called the pooled variance. Remember we had a pooled proportion? I didn't test you on that when we compared proportions in chapter 9. I didn't test you on it, but I talked briefly in class about a pooled proportion. In chapter 10, there's a pooled variance. That's what the P stands for here. So many P's in this class. Probability, population, parameter, proportion. Pooled. Okay, that P stands for pooled. Find a 90% confidence interval to estimate mu1 minus mu2. For what purpose? To compare mu1 and mu2. Also, do they say do a test? No, but they do ask what theorem are we using to do a T procedure. I will do a hypothesis test as well here. Let's do the confidence interval first. Here is a 100 times 1 minus alpha % confidence interval to estimate the difference of two means, two population means, mu1 minus mu2. What's, first of all, a natural logical point estimator How about x1 bar minus x2 bar? Right? Nice and logical, natural point estimator. You might wonder, is it unbiased? And the answer is yes, it is, because x1 is x1 bar is unbiased estimator from u1, and x2 bar is an unbiased estimator from u2. We should emphasize that here. The expected value of x1 bar minus x2 bar is the expected value of x1 bar minus the expected value of x2 bar. That's a property of expectation. And that's mu1 minus mu2. Okay? Because we know that's an unbiased estimator from mu1, and this is an unbiased estimator from mu2. So the difference is an unbiased estimator for mu1 minus mu2. What about the variance? I haven't written the rest of the confidence interval here yet. Independence implies the variance of the difference is the sum of the variances. I talked about this before the test as well with proportions. Independence of these random variables, which is an assumption in the theory we're doing. We're assuming we got independent random samples from these two different populations. And those variances are, well, from chapter 7, sigma 1 squared over n1 plus sigma 2 squared over n2. Coming back to the confidence interval, what's the margin of error? We're going back to means here instead of proportions. Maybe that means we need to go back to t instead of z. Yeah. T sub alpha over 2 times an estimator for this, the standard deviation of x1 bar minus x2 bar. The standard deviation is the square root of this thing. What's a natural estimator for that? I could replace sigma 1 squared with s1 squared and sigma 2 squared with s2 squared. But maybe I'll get a better estimate for things if there's no reason to assume these are different by pooling. And I already did the test for whether sigma 1 squared equals sigma 2 squared, and I did not reject the null. Let's go ahead and pool. Let's replace both sigma 1 squared and sigma 2 squared with sp squared. I haven't said what the pooled proportion is yet, but I could make that replacement. Then I could factor out the sp squared and write it like this. The main benefit of doing this in this way, the main benefit of pooling these two variances is that the degrees of freedom you use is simpler. Degrees of freedom is going to be n1 minus 1 plus n2 minus 1, it turns out, which simplifies to n1 plus n2 minus 2. I'm not explaining why, that's just what it turns out to be. If you don't pool, if you have good reason not to pool, you do end up replacing sigma 1 squared with s1 squared and sigma 2 squared with s2 squared, and the degrees of freedom becomes much more complicated. It involves something, if you use a formula, called the Smith-Satterthwaite formula. And I guess I should show that to you in all its glory. It is in the book. I think I'd used this formula once without making a mistake. Once in my life. I tried a few other times and I made a mistake every time. That's the degrees of freedom if sigma 1 squared and sigma 2 squared are clearly different. What in the world? And it's an approximation. It's not exact. There's a dot above that equal sign, and that's not a bug. There's a dot there that's approximately equal to each other. It doesn't give you a whole number, so what you end up doing is rounding up if you use a table. Yeah, I think I've used that once in my life without making a mistake. Do you have to use that? No, you don't have to use that. You can use technology instead. So either pool or use technology, but I haven't told you yet how to find the pooled proportion. It's a weighted average of the individual proportions. it turns out to be a weighted average in kind of a funny way. It's n1 minus 1 times s1 squared plus n2 minus 1 times s2 squared divided by n1 plus n2 minus 2. Kind of a weird weighted average, but that turns out to be the best thing to choose to make this an unbiased estimator for the population proportions if you assume they're equal. Okay, so we kind of like this approach. As far as using it, I mean, you certainly can plug all the numbers in that we have here. Do I want to take the time to do so? Probably not, because I want to get onto regression. But maybe I'll plug in the summary statistics at least. If we were trying to compute this confidence interval based on the summary statistics that we see in this problem statement, we'd want to go to the stat menu and go to tests. We're not doing a hypothesis test yet. We are after an interval, a two-sample T interval. And it's not for a proportion, so we don't use the prop one. We use a two-sample T interval. That's the implicit assumption when using that part of the menu here, is that we are getting a confidence interval for the difference of two means using a T statistic, because we don't know the population variances. We are using sample variances. I could use data if I had data, but I don't have data. I've got stats. X1 bar, look at the problem statement here, is 40. S1 is, well, careful, square root of 24.9, right? The problem statement is giving me a variance, but the calculator wants a standard deviation. N1 is 61. X2 bar is 29. S2 is square root of 22.7. And N2 is 61. Confidence level is set at 95%. We are asked for a 90% confidence interval in the problem statement. Should we pool or not? We're choosing yes, because we're making the assumption that sigma 1 squared equals sigma 2 squared. If we didn't have good reason for that, then we choose no. By choosing yes, we're using the formula that I wrote down. If we choose no, then we would use the other formula, and the degrees of freedom, again, would be much more complicated. So we should be able to get a confidence interval here. And maybe it'll say the degrees of freedom is n1 plus n2 minus 2. It should say maybe 120 degrees of freedom. 61 plus 61 minus 2. There's our confidence interval. And does it say degrees of freedom is 120? It doesn't say it, but that is what it's using. Notice it's giving us S1 and S2. It's also giving us the pooled standard deviation in this case. And there's the confidence interval, and the calculator is using this to estimate. Okay, we're estimating a mean. We're saying the difference of the two means, we're pretty confident, 90% confident, is between about 9.5 and 12.5. The point estimate for this difference is 40 minus 29, 11. Right, this interval is centered on 11. 11 plus or minus about 1.5. The margin of error is about 1.5. If we had not pooled, what would we do different? Well, we just go down here and say, don't pool. No. We would get a slightly different answer. Yeah, ever so slightly different. And notice it is saying in degrees of freedom. That's not exactly 120, though it's close. Not significantly different to make much of a difference, it seems. The Smith-Satterthwaite formula evidently is what's being used there. But you'd round up to 120 anyway if you're going to use a table. There are some circumstances where the Smith-Satterthwaite gives you a pretty significantly different degrees of freedom than n1 plus n2 minus 2. And it's technically what you'd want to use if there's no good reason to assume the population variances are the same. Can we do hypothesis testing? Yep. Test the null hypothesis that mu1 equals mu2 versus the alternative that, well, it seems to make the most sense in this case, that mu1 is bigger than mu2. There's a z-stat we could use, a t-stat, excuse me. T sub n1 plus n2 minus 2, that's the degrees of freedom. It's the point estimator, x1 bar minus x2 bar minus 0. 0 is the null value. I put the 0 in parentheses there, sort of by accident. I didn't really mean to. Divided by a standard deviation approximation. Use the pooled variance again. Do this kind of thing again. If we did not pool, then the test statistics are a little different. Once again, the degrees of freedom to use here is n1 plus n2 minus 2 when we pool. If you don't pool, then you use Smith-Satterthwaite. How does the test turn out for this example? Now in my stat menu, instead of interval, I'm after two sample t-test. Looks like my numbers are still in there though. It's a right-tailed test. If I pool, what happens? What kind of p-value do I get? Maybe we also want to draw it. It's going to draw an error area. That's evidently a t-distribution with 120 degrees of freedom. It's saying p is essentially 0 because the test stat is very large, 12.45. Is the p truly 0? No, it's probably like 10 to the negative 50 or something, but so close to 0 that it's saying effectively it's 0. Definitely reject the null. If we were doing a two-tailed test, we'd want to double the one-tailed p-value. 2 times 0 is still 0. Okay, 2 times 10 to the negative 50 is still very, very small. We'd still reject. Yeah, that makes sense with the interval. The interval was very far away from 0. In fact, whenever you're doing two-tailed tests, not equal to in the alternative hypothesis, it's basically equivalent to doing a confidence interval and seeing whether 0 is in the interval or not. Our confidence interval was pretty far from 0. 9.5 to 12.5 or so. 0 was far from being in the interval. It only contained positive numbers. Strong evidence that mu1 is bigger than mu2 from a confidence interval perspective. We're also rejecting the null that mu1 equals mu2. So again, I'm not going to test you on this, but probably you will go and review this in applied stats in more depth and probably have homework problems on it, I'm guessing. I'll tell Dr. Wetzel that we didn't do much depth on chapter 10 here. So I'm thinking he probably will cover it. It would be good to cover. Go into more depth, get more practice with it. It is a very useful, it is very commonly used content, chapter 10. Out there in the workforce, you might even say it's the most common kind of thing to do, comparing means. In the workforce, the most common kind of statistical test to do.